Today, what I want to talk about is a little of 9.2 and 9.3. These are going to be our final collection of topics. So chapter 9 is all about differential equations. We'll cover that. And I'm going to sprinkle in at the end a few other integration techniques that are BC topics, but I think would be standard Calc 2 fare that you'd expect to see in your college Calc 2 classroom that I'd like to do to give you a little bit of exposure there. I think I'm looking at probably 3 other like BC topics: integration by parts, improper integrals, and trigonometric substitutions, which are 3 pretty standard integration techniques that you would see in a Calc 2 classroom and then would follow, in any other calculus classroom past that. These would be pretty standard techniques to use. Yeah. So let's start by talking about what we mean by a differential equation. So you guys remember way back in semester 1 when we did implicit differentiation?
Yes. Yeah.
Right, where we had x and y's on the same side of the equation, we took the derivative. Differential equation is like the other side to that coin. So it's going to be here's your implicit derivative. Can you now recover the original function from that? Okay, so it's going to be like finding the antiderivative to one of these implicitly defined functions. So for example, if we say that y prime is equal to x plus y, that's what we'd consider a differential equation. Is everybody okay with that? So if we're looking for the solution to that differential equation, like the y equals whatever, the original formula, and we know that the original equation, the solution, passes through the point 0, 1, we have enough information right now to sketch what that solution would look like, just from the differential equation and the 1 point. So the way that we're going to do that is we're going to create something called a slope field or a direction field. You could use those 2 terms interchangeably. And then we're going to use that as a guide to sketch our solution. Everybody's okay with that plan? And the only criteria for that solution that we sketch, it's going to be guided by the slope field, but it needs to pass through that point 0, 1. So far, so good? Okay. So what I'm going to do now is I'm going to start with an xy axis like we have here. And I'm going to look at the lattice points. The lattice points are just the whole number xy coordinates. 1, 1 is a lattice point, or 0, 0, or 3, 4. Those are all considered lattice points. 2.5, 1.6 is not a lattice point. So we're just going to look at the whole number points. Everybody cool with that? So for example, 2, -1 is one of these lattice points. If I take the x value of 2 and the y value of -1 and we plug in to our differential equation, I'd have 2 plus -1, which is equal to 1, which tells me the slope of y at the point 2, -1 is 1. So on my xy axis, I'm going to put a point at 2, -1, and I'm just going to sketch in a little tiny line that looks like it has slope of +1. Everybody's okay with this? And I'm going to do this for all of my lattice points. Now, I'm not going to ask you to do this by hand because it stinks, it's really time consuming. The AP would not ask you to do this by hand because it stinks and it's really time consuming. What I will do is give you a delta math assignment where we give you a situation where everything is pre-made and we're just going to kind of have to adjust the slopes at each lattice point to create our slope field. Does everybody feel okay there? So for this example, if I have the point 0, 0, if I plug 0 in for x and 0 in for y, what do I get? 0, right? So I'm just going to take this and adjust it so it has 0 slope. If I take the point -1, 0, what is the slope going to be there? 0 again, right? If I take the point -2, 0, 0 again. If I take the point 0, -1, that's also going to give me slope 0. How about 0, -2? Slope 0, so I'll adjust that. So I just really have 4 more to calculate, right? So if I have -1, -1, I'm going to get +1, right? -1 times, or then make it negative is positive, and -1 squared is positive. And that looks like a slope of +1 to me, right? If I have -1, -2, the slope there would be +4. So I need to make that a little steeper, maybe there. Okay, I'm just kind of estimating. Okay, there's no rhyme or reason. I just kind of, it's got to be steeper than slope 1, which should be like a 45-degree angle. So I'm just going to make it steeper. If I look at -2, -1, the slope there should be +2, right? Negative of -2 is +2, and then -1 squared is 1. So I need to make that steeper than this one, but not as steep as this one. So maybe like there. Does that look okay? And the last one is -2, -2. The slope there should be +8, right? So their steepest one yet, so just shy of vertical. I'll do that. I'll hit submit. Hopefully we were close enough. Marks it correct. So there they drew in the actual slopes, and you saw that, like, okay, I was pretty close. Does that feel okay? So I think it's okay to assign you to do this by hand with the computer's help. Doing it by hand yourself is just like an exercise in tedium, right? Like, it's not difficult to do, but it's time consuming, and you have to be kind of neat, and it's easy to make a mistake, and like there's a lot of erasing involved, and just like it just is one of those where it's like, oh my God, I get it. So I think doing it here this way is a much better way of doing it, and you get the same thing out of it, right? Does everybody feel okay about how we constructed the slope field? Perfect. So back to this. So I do that for, so here's the slope field for that, for something, or for that problem we were just looking at. So this is the slope field that ends up generating from this differential equation, y prime is equal to x plus y. Now if I add in the point 0, 1, which is what I'm given here, so I'll plot that wherever my pen went. Where did my pen go? That's a problem. Who stole it? Did you take it? Where the heck would that have gone to? Is that in my pocket? Ah, there you are. So I'll plot the point 0, 1. Looks like maybe it was right there. Everybody's okay? So I'm just going to now use that point and the slope field to just kind of like sketch in my slope, which would kind of look like that. I'm just kind of trying to follow the slopes on the slope field, right? So like here it's like to there, and then we're getting a little bit steeper, and then like a little bit steeper and a little bit steeper. Do you kind of see that, Meredith? So I'm just kind of like just filling the space provided. And if I start going this way, it starts like, you know, it's much less slope. You kind of see what I'm saying? Okay. Again, like doing this by hand is kind of stinky. But if we, again, give you the delta math. So it says, okay, here's your differential equation. Here's the slope field. We have the 0.5, -3, which they've already put in for us. And now we're just going to kind of be sketching in the solution to this. So I'm just going to use the slope field as kind of my guide. So here it looks like I get vertical pretty quick, right? Pretty steep. And then here I'm going to be, following until I get like, ooh, pretty steep. Oh boy. Undo last. Okay. Well, that stinks, but okay, I can deal with that. And I'll say, okay, that's my sketch. They'll either say it's close enough or not. It says good enough. So the red is the actual solution. And you notice that that probably would have been, there's the comparison of the actual solution versus mine. They said, okay, close enough. And that's what this will be. Do you guys feel okay doing this? Again, there's not like a specific method to be doing this. It's just kind of using our eyeballs to kind of look at what's going on here and just match what we're seeing. Does that seem okay? And I like doing this as the delta math because it's going to give you a feedback right away of like, that was close enough or not close enough, or like, how close was I, right? Like, that's pretty nice. Okay. Back to home. And then we can do this like with a discontinuity in here. So if I look at it's doing the exact same thing, and just now like we kind of have some asymptotic behavior in here. If I look at this, it looks like there's a vertical asymptote here. Notice the straight vertical slopes, right? And it looks like as I move along the x-axis, we're leveling out to no slope, right? So the slope is slowly getting flatter and flatter and flatter as I move. So I'm going to look like probably one of these guys. And then we'll be following down to like here. And then coming back out up, I don't know, something like that. And hit check and see if it says I'm close enough. Oh, it wasn't close enough. So let's undo some of that and try it again. Try that and see if it takes it. Nope, didn't. Oh, it didn't want anything past that, huh?
So do you just go to the end of the graph?
Yeah, I guess that there's, okay. So if there's a vertical asymptote, you're not going to put anything on the other side of the vertical asymptote, I guess is the takeaway here. So had I not done that, I probably would have, it might have taken it, might not if I was off up here. But I think the bigger issue was I had stuff on the other side of the vertical asymptote. Yeah. Anyway, that's the idea on that one. That's fine. Probably the most difficult type of problem that we're going to ask you to do here is going to be matching the slope field to the differential equation. This is 100% AP multiple choice question you will see. So they'll give you a slope field and a differential equation, or they could do it the reverse and give you the differential equation and a bunch of slope fields. I've seen it presented either way. But this is 100% a problem that you'll get. So when I look at a slope field like this, first thing I'm going to do is I'm going to look for stationary values. So is there a value for x or y where the slope is horizontal?
Yeah.
Yes. Looks like right here, this specific value for x equals 0, gives me a horizontal slope, right? Everybody see that? So I know immediately I can discard this option, because if x equals 0 here, this should be vertical, undefined, right? The other ones seem fine, because if x is 0, I get 0, 0, 0. Those are all good, right? The next thing I'm going to look for is if y is -3, this one should give me 0, but these ones would be undefined, right? So let's look at what's happening at -3. Am I getting a 0 slope at y equals -3?
Yeah.
That's vertical slope, right? So this one is out, right? So now it's just a choice between these two. Everybody agree? If I compare these, this one is something squared on top and something squared on bottom, which tells me the slope here always must be positive. So let me look at the slopes up here, and if I see any negative slope, I know that it's done for.
It's not the top.
All of these slopes look like they're all positive, right?
Right.
Everywhere the slope diagram is. So that's the one I'm going to want. This one, if like say we were in, somewhere over here where the x coordinate is negative, the y coordinate always has to be positive. Over here, the slope would have to be negative for this one. So that's all I'm looking at when I'm looking at these things. I'm just trying to do it by elimination. Yes, sir?
Can I grab Marcelino for a minute?
Yeah. Let's do another one of these though, because these can get tricky, right?
Yeah. Yeah.
Okay. All right. Do you guys see any horizontal pieces?
Yeah.
Okay, where do you see a horizontal slopes at? At x equals 6? Well, at x equals 6, it's not always horizontal, right? Because I have some stuff down here where it's not. Y equals 0, right? All straight across here, and the line y equals 0, we have a horizontal slope. So that tells me that I can get rid of this one and this one, because if y equals 0, those should be undefined. I can discard those two immediately. Everybody good? Okay. If I look at these two, this one should be at x equals -4, I should have slope 0. This one at x equals -4, I should have slope vertical. Let's look at what happens at x equals -4. What do I got? Vertical. So I'm going to take this one. Does that feel okay?
Is it vertical because it was in the...
Yes. Yeah, undefined is vertical slope. Does that feel okay? Everybody else okay? These are good questions. All right, this next one I'm going to put up here and sit for a minute and let you guys think about it. Notice that I don't really have to write anything down. to do these. If I zoom in too much, I lose the answers or the number or the equations and the picture. But this is as good as I can do for you. I'm sorry, that can't get any further. Now when I ask for an answer, I'm gonna expect every single person at some point to raise their hand for either A, B, C, or D. There's no abstaining. Okay, so everybody I want to participate here. Not that I'm trying to like make this hard on you, but I think it matters, right? This is something that can be difficult, but doesn't need to be. All right, should we talk about this one, or do you guys will want a minute? All right. Who picked this one? Show of hands. How about this one? Okay. How about this one? How about this one? This is our answer. So if you pick that one, good job. Again, the toughest to pick between would have been these two, correct?
Yeah.
You should have seen y equals 0 as a horizontal piece, which makes sense because the y's are in the numerator. And then x equals 3 is a vertical slope, which makes sense because I have x minus 3 in the denominators. So what I would have looked for here is on this one, everything where x is less than 3 should be a positive slope because I'm going to have a negative in the denominator, a positive in the numerator, and then a negative out front. So 2 negatives makes a positive. But if I look at this section over here, I see negative slopes. And this is less than 3. Does everybody see that? Or if I was looking for this one, I would say, okay, well, as long as y is positive, I should have positive slopes. And if y is negative, I should have negative slopes, since the denominator is always positive. And if I look up here, all of these guys are positive, and all of these guys are negative, so I feel real good about where I'm at. Does that feel okay? If you ever get stuck or hung up, you can always, like, if it's hard for you to do what I just did there, if it's like, ooh, that's not obvious to me, you can pick specific points. Like you can pick, like if I look at this point, that looks like the slope is -1 there, right? Or thereabouts. I can take the point 2, -1 and plug it in here and see which one gives me a slope that's closest to, looks like -1. And that's also an effective way of doing this, although a little bit more computational. You have to probably write something down or type something into your calculator, or at least do some arithmetic in your head. I like just looking at the picture, but that's an entirely valid approach to just like pick some test value, like narrow it down the best you can, and then pick some test values until like, okay, that's definitely the different, those two are definitely different. And the slope that I'm getting from this one matches the slope I'm seeing in the picture. You know what I mean? In this case, this one would have given you a positive slope, and this one would have given you a negative slope, and that should have been enough to make your decision right there. That's a bit. let's do one more and then we'll kind of keep on going forward. Does that sound okay to you guys? Does this feel okay though with what we're doing here? Again, it's one that just like getting some practice and things will go better. There's some of this in the bookwork as well. Sometimes these things can get like, the functions they give you can be kind of complicated. And I don't think the delta math ones ever get super complicated looking, but I'll let you again take a look at this and then we'll kind of go through it here as a group. You guys got it, or do you need a minute still? Yeah, take a minute. It's okay. Again, this is the first time you're doing this, so it's okay to be like hesitant and need some more time to really kind of think through it. It's okay. Who says this one? Show of hands. Okay. Who says this one? Okay. Who says this one? Okay. And who says this one? Okay. So first thing we look for are the horizontal or verticals, right? So I see horizontal at y equals 1 and horizontal at x equals 1. So I can immediately discard the two fraction ones, because there I'd have vertical at y equals 1 and vertical at y equals 1. So I know it's going to be one of these two boys. Everybody okay with how I concluded that right away? If I look at this one, x minus 1 squared is always positive, and y minus 1 squared is always positive. So the slope here should always be positive. I see a negative slope right there, so it cannot be this one. Has to be that one.
How do you know that it's always going to be positive?
Because I had something squared times something squared. Something squared is always positive, right?
Yeah.
Is that?
Yeah.
Okay. So that's matching things to slope fields. That's basically the gist of like what the AP would be asking you to do with this. They might ask you to sketch a solution in a onto a slope field on like a free response question. That happens on occasion. More often than not, they're just going to be matching the differential equation to its slope field. One way or the other, either slope field to equation or equation to slope fields. I've seen it presented either way. Do you guys feel pretty good so far? Okay. So that's it for 9.2. I'm not going to do anything more on the notes. I just basically wanted to talk about what these things were and give you like some delta math exampling of how you do them. But like that's the kind of problems that are in the book work are the same things that are on these delta maths. I've posted that delta math I just showed you guys. You don't have to do it, but if you want the practice, I think it's good. It gives you feedback right away. They're pretty simple in terms of like what you have to do. There's not a lot of algebra because it's kind of, is this close enough kind of work? It's nice to get the immediate feedback. So I put that in there for you guys to use for practice if you'd like. Not an assignment, not due, but it's there if you'd like. Highly recommended, but I don't need you to do it. You know what I mean? Okay. What we're going to do now is like do the algebraic version of this now. So it's going to be like, okay, how do I really recover that original function? So there's different types of differential equations depending on how separable they are. We'll talk about first order differential equations. So first order means that it's just first derivatives living in it instead of second or thirds also. And separable means that I can separate the x variables and the dx onto one side and the y variables and the dy onto the other side and have function of x times dx equals function of y times dy. That's what I mean by that's what we mean by separable, is that we're able to do that. We'll look at another situation which they're not separable and how we cope with that later. So that's basically going to be my strategy. So let's look at the differential equation dy dx equals x squared over y squared. So my goal is to get a function of y times dy on one side and then a function of x times dx on the other side. So if I look at this, if I multiply both sides by dx, I'd have dy equals x squared over y squared times dx. Does everybody feel okay with what I did there? And then if I multiply both sides by y squared, I'd have y squared dy equals x squared dx. Yep, that's the same thing that we're doing. I'm just kind of like trying to go slow and not over algebra you guys right away. But in some situations you won't want to cross multiply. This one would have been fine to do that. Once we've done that, then we can just integrate both sides. What's the antiderivative of y squared? Okay. And the antiderivative of x squared? Yep, same thing but x's. And then I need something else here. Plus c. Very good. And then, so that's like part A.
Why would you do plus c on both sides?
Because then if you subtract c from both sides, it's 0. So technically speaking, Aaron, when we do this, we have like a c1 over here on this side, and then like a different c on this side. And then if I subtract, say, c2 to both sides, I have something like this. And c1 minus c2, well, that's still just a constant, right? So we just put one c on one of the sides and call it good. Does that make sense as to like what happened?
Yeah.
As why there's just one c and just y to go on, and it doesn't matter which side you put it on. Okay? Now to do part B, it says that we need to use the boundary condition or the initial condition. Y of 0 is equal to 2. What that's saying is that when x is 0, y is 2, right? Okay? So if I take that here, we have 2 cubed over 3 plus c equals 0 cubed over 3. So c is negative 8/3. So I can say that. And now if I wanted to, I could clean this up, but technically you're done at this point. Like if I multiply through by 3, we can do that, right? And if I wanted to, I can move the, like add the 8 over, and then I could like cube root both sides or something. And I could write it as a function of y now if I wanted to. But like, as far as I'm concerned, those last 4 are all equivalent, and all you're doing is like rearranging things. If they don't specify that you need to solve this as a function of x or a function of y or whatever, then I think any step along the way is appropriate and correct. Certainly. Does everybody feel okay with what we did? Okay, we're just going to keep banging out examples of this process here. Okay? This is all a 9.2 or 9.3 is. It's just basically examples of this. How do I separate this differential equation? Peyton? Yeah, we can just like cross multiply, because notice the x's are on a diagonal with each other and the y's are on a diagonal with each other. And we'll just integrate both sides. The antiderivative of 2y is y squared. And the antiderivative of cosine is sine. And I'm just going to put the plus c on this side because it's got to go somewhere. And the antiderivative of 6x squared would be 2x cubed. And we just, good enough. It's done. Notice this one that it would be impossible to get the y by itself, since you have the y in both a polynomial and a cosine, or a sine function. You're not going to be able to get a y by itself here, but this is good. Feel okay? Not a big deal, right? The hardest part is making sure you've got things separated correctly, but after that, it's just like pretty much easy integrals. Okay. Here it says y prime is equal to x squared y. So again, I like to think about everything in terms of dy dx's, so I'm just going to rewrite y prime as dy dx. What am I going to need to do to separate this guy? Good, multiply by dx. And then we'll divide by y. I'll write as 1 over y if that's okay with everybody else. Oops. Feel good? We're separated, so we can integrate both sides. What's the integral of 1 over y? Good. And the antiderivative of x squared is? Forgot a c on the other side, so I'll just put it on this side, I guess. And if I wanted to, I could separate the y out here, right? I could do like base e to both sides. So that would be like absolute value y equals e to the x cubed over 3 plus c. Now, we typically wouldn't write it this way, specifically the plus c and the exponent. If you remember your rules of exponents, addition the exponent is the same thing as like multiplication of things with like bases, right? What is e to the c going to be? That's just a constant. So what they're going to do is they'll write it as like this way. Since e to the c is just a constant, let's just call it c again. You could use a different letter if it bothers you that it's c twice. You could call it k or, whatever, a different letter if you like. But I needed to show you that because that's something that like the back of the book would surely do on you. And you'd be like, where the heck is this? Why is it multiplied? Mine is in the exponent. It's like, oh, it's the same thing. Or where did this e come from, right? But this is basically the gist of it. Does this feel okay? Yeah. All right, we're stopping here. It's 2 sections in one day. I think that's plenty. So the homework for 9.3 and 9.2, 9.3 is 1 through 17 odds, and then 19 to 24. And then 9.2 was just like whatever, just odds here. I think 19 to 20, or 1 through 8, and then 19 to 23 odd. Actually, I want to check that real quick because there's Euler's method stuff in here, and I don't actually want to do that this year. I don't think it's worth. It's another BC topic that I think is less important than some of the other BC topics that I'd like to spend time on, so I don't know that I don't really want to do that. And if I assigned Euler's method problems, I want to back those out here real quick. Yes, I did. So we'll actually get rid of that. So just 1 through 8. And then the other problems from the other set. I'll update that on minor name and stuff to reflect that I threw those guys out. But that's it for me. That was 42 minutes for 2 sections. And I think you guys felt pretty good about what we did here.
Yeah.
Yeah. Good.
So this is our last unit?
This will be the last unit. Will be these differential equation problems and then some other advanced integration technique.
Okay.
And that'll be the last unit. We should wrap that up, mid-April, I would hope. We'll talk about it, see what you guys feel. Personally, I think we'll have done enough I'll feel fine either way, but we'll see what you guys want to do. Yeah.